And then we'll look at the reactions. The reactions parallel those for alkenes very nicely, except there aren't a whole lot that we'll talk about. And then we're going to do an introduction to synthesis. Synthesis is one of the high points of organic chemistry. It allows you to think backwards. And it's actually the skill that many pre-professional schools look for in terms of why you take organic chemistry. They really don't care so much that you know the reactions of alkenes, but synthetic logic really is kind of important. It's a problem-solving skill, and this is just a very nice academic way to develop it and to test it. So we're going to do an intro to organic synthesis. We talked about hybridization in carbon. If we have an alkane, we said that this is an sp3 hybrid. We have 4 bonds to our carbon. They're all equivalent. These are classic single bonds in methane. Double bond, we build from an sp squared hybrid. That leaves 2 p orbitals left over, 1 on each carbon. These overlap, and that gives us our second bond, simple alkene. And alkyne, we have a triple bond. Again, this is an sp hybrid, 1s, 1p. Leaves 2 p orbitals on each carbon atom. These overlap to make our triple bond. In a little more detail, this is how we construct the thing. Our sigma network comes from 1s and 1p. We have 2 bonds, therefore valence shell electron pair repulsion would predict that we would have linear geometry. Again, we have 2 p orbitals left over. One pair on each carbon, and these guys overlap very nicely to form molecular orbitals either above and below or on the side of the sigma network. Now, because this is linear, you actually could never tell if we had free rotation or not, but we don't, because once again we have to keep these orbitals aligned in order to get good overlap. As these things overlap, they generate what we refer to as our triple bond. Any questions about where these things come from? Yeah?
Technically, you don't always have to have a triple bond to be sp hybridized. Can you have a double bond?
No. Double bonds are always going to be trigonal, sp squared. Triple bonds, even in something like a nitrile, carbon nitrogen, is still considered a triple bond. Yeah. Just like with alkenes, if you look at the electrostatic potential map, we expect the reactivity to be here in this pi system because this is where the electrons are. The reactions that we'll look at are going to be very similar to those of alkenes, but there are just a few differences and a couple really neat things about alkynes. First, let's go ahead and name them. If we're looking at an alkyne, our first step is going to be find our triple bond, and we're going to identify the longest continuous carbon chain that contains the alkyne. We want to number the thing, giving our alkyne carbons the lowest possible number, and then we're going to simply name substituents. If we have more than one triple bond, we would call it a diene or a triene, whatever. For this one here, we look and we see we have our triple bond here. That would give us our longest continuous chain. A mistake that people make sometimes when they're looking at triple bonds, don't forget that this is a carbon, and if it's written this way, we assume that there's a hydrogen attached, okay? So we have 1, 2, 3, 4, 5 carbons. We'll start numbering down here with our triple bond, because that will give it the lowest possible number. So we have a pentyne here. We have to put a number in to show where the triple bond is. So this is a 1 pentyne. We also have an ethyl group down here attached to carbon 3. Just like naming a simple alkene, we'll stick this in front. 3 ethyl, 1 pentyne. Any questions?
So, since it's on the first, what makes it different for not having the 1 versus putting in the 1? Like for the triple bond, I remember on the double bonds, for the alkynes,
Yeah.
you didn't always throw in the 1.
You don't throw in the 1 on an alkene if it's in a ring. That's a cycloalkene. You don't need to put it there, but for a straight chain you do. Same thing with alkynes. If we had a molecule that had both an alkene and an alkyne, well, there has to be a rule. And the nomenclature gets a little ugly. We probably won't have things like this on the second hour exam. But the rule is that the alkene gets the credit, alkene gets the highest priority if there's no difference in the numbering. So in this molecule, we have an alkene on one end and alkyne on the other. The rule is we're going to give the alkene the lowest number, so we're going to number this way. We have 8 carbons. We have a double bond here in carbon 1. So this starts off as a 1-octene. Now we have to somehow show that we have 2 functional groups. What we're going to do is drop the E out here. And we're going to indicate that at carbon 7 we have an alkyne. Dropping our E, putting in our alkyne, 1-octene, 7-ine. Now again, we're not going to do this on the exam, but as you can imagine, nomenclature can get fairly complicated if we have multiple functional groups. When we get to things like alcohols, and we have, say, a long chain and an OH somewhere, we're going to do the same thing here. Let's just stick in the number OL. So just remember that this can happen. If we have a molecule like this one, now there's a difference. So our alkyne is going to get the lowest number. This is going to be a 1-octene down here. And in carbon 6, we have a double bond. So that would be 6-octene, 1-ine. Now, as you can imagine, on this next exam, we're going to have plenty of stuff to test on. Nomenclature isn't going to be a major part. Yeah.
Is there going to be a quiz before?
Yep, quiz is going to go online today, and will stay up until the day of your exam. Just for the heck of it, the Nomenclature question for alkynes that was on the exam was this one. Oh, I forgot to say, this name has something missing, doesn't it?
Yeah.
Because we have stereochemistry around our double bond. We need to indicate if this is E or Z. Which is it?
E.
Well, you saw it on the slide. Back in the old days, we would call this trans, wouldn't we? We remember that by the new rules, this is E. The highest priority groups are on opposite sides of our double bond. So what is this?
Something that we never named before.
This is very difficult. We would have a diol. We have stereochemistry. We have stereochemistry around our double bonds. This one too. And we have 2 triple bonds. This is hemlock. Yeah, it's the poison that Socrates drank and whatever. Very toxic molecule. Natural products can be very, very complicated, as you can see. All right, reactions of alkynes. Basically, we're going to have 2 sets we're going to look at. We're going to add HX to our triple bond. That's going to be just like the addition to an alkene. We're going to describe the regiochemistry as Markovnikov. And the only difference is, instead of adding 1 mole, we're going to add 2. Both halogens will go on the same carbon. We're going to do these later. This is just an overview. Addition of, say, bromine or chlorine to a triple bond. Just like an alkene, except it happens twice. So we wind up with 4 halogens in our molecule. We get a little bit different here when we do hydration. Hydration of an alkyne only occurs in the presence of mercury. And we wind up with a carbonyl compound. Now, we'll go through this, explain how it happens, but this actually follows Markovnikov regiochemistry very closely, very simply. Same thing here with hydroboration oxidation, anti-Markovnikov. Both of these have an enol intermediate. Reduction. With an alkyne, you can do reduction 3 ways. Alkenes were boring, they just went to the alkane. Here we could go all the way to the alkane. We can stop halfway to give syn addition. We can stop halfway to give trans addition. So all 3 of these we will talk about. And finally, the one that's a new class of reactions for us is going to be a simple alkyne alkylation. We'll talk about this one first, actually, because it's a new class of reactions for us. But what we'll do is take a very strong base, sodium amide. We'll actually pull the hydrogen off of here. That makes it an anion. The anion will then attack an alkyl halide, and we'll just add the anion or the alkyl halide group onto the end of our alkyne. So it's a new class of substitution reaction that we didn't see with alkenes. Let's go ahead and talk a little bit more about this one. The base that we're going to use is sodium amide. Sodium amide is something that you make by taking sodium, solid sodium, and you add it to liquid ammonia. Liquid ammonia is a lot like water. And when the sodium hits it, it fizzes, just like sodium does in water. As it does, well, with water you would get hydroxide, wouldn't you? Here, all we do is lose the hydrogen, and we make NH2 minus. Very, very strong base. Much, much stronger than hydroxide. All right, the alkyne hydrogen itself is mildly acidic. Its pKa is about 19. Remember, water is about 16, 15.74. So it is less acidic than water, but it is still acidic enough that something like sodium amide can pull off this hydrogen to give us the anion. So step one in this reaction is to make your alkyne anion. Now back in chapter 5, we talked about nucleophilic reactions. We said we were going to have a nucleophile and we were going to have an electrophile. In this, the nucleophile is simply the alkyne anion. Nucleophile looking for something positive. This is our electrophile. This is a polar covalent bond, partial positive here on this carbon. So the nucleophile is simply going to attack the electrophilic carbon. Iodide leaves. We now just take whatever was attached here and stick it on the end of our alkyne. Very simple substitution reaction. You can do this with virtually any primary alkyl halide. If we start getting things attached here, more carbons, it doesn't work so well. Secondary and tertiary don't work very well. But if it's a primary or a methyl, this can work very nicely. Yeah?
Before it attaches to the CH3, what's the sodium protection?
Sodium winds up as sodium iodide.
I know, but like before it's attached to the.
Oh, this is just an ion pair here.
Oh.
So we have the anion negative and the cation sodium. There's, of course, a movie for this. The reaction we're going to have in the movie here, we're taking the anion from propyne. We will attack chloromethane. Again, our nucleophile, the electrophile, lose the chloride. Remember, we saw in chapter 5, or chapter 6 maybe, this really neat animation of a reaction like something like this. And the thing that we noted was that in the transition state, in the middle of this reaction, that this carbon goes planar. So this attacks, this leaves at the same time. In the middle, this is planar, and we wind up with this as our product. Let's see if our movie plays. No, it didn't. We'll try it again. There it goes. Here's the alkyne anion. It's going to attack. Chloride is going to leave. Here's our transition state. See, it's planar. Bond makes, bond breaks. And all we do is attach the methyl group to our nucleophile. Bond making, bond breaking, there's the transition state. And this is our product. Any questions? All right, well, like I said, this is the only new class of reactions. Let's go ahead and go through the list of the old ones. Remember, we're dealing here with a triple bond. So for the first couple we look at, we're going to simply do the same thing we did with alkenes twice. Here's our triple bond. We're going to react it with HCl. We're going to wind up with a dihalide, and the halogens are going to be attached to the Markovnikov carbon. That is the carbon that would give us the most stable carbocation. So if we look at this, this is attached to our triple bond and to a hydrogen. This is attached to our triple bond and to a carbon. So this guy would be the most stable carbocation. That's all you have to do. And then remember, you're going to add 2 chlorides to this, 2 hydrogens to this one. The reaction actually involves this guy as an intermediate. So this is what happens after we add 1 mole of HCl. If you think about it, in the vinyl halide, again, let's do the Markovnikov thing. This is attached to our double bonds and just hydrogens. Now we are attached to a carbon. But remember, this chlorine has extra unshared electrons, doesn't it? So that means that this would be a super stable carbocation. So once you get to this stage, there's no question, the second chlorine is going to come here to give us the 1,1 dihalide. So just like alkenes, except twice.
So don't worry about the rings.
About
Wouldn't
the
you
ring?
want to attach it to the ring because it's the most stable?
No, we're going to simply look at our triple bond. Once we add the first halogen, there's no question. We're only the second one must go here. Resonance stabilized carbocation. Yeah.
So the 2 hydrogens go to the first carbon and the chlorines over this. I guess I don't see the difference in stability between the 2 carbons.
Well, if you just think about Markovnikov's rule, remember Markovnikov counted hydrogens. The carbon that has the most hydrogens gets the hydrogen. So think about it that way, but in fact it is carbocation that you're thinking about. Addition of something like bromine, once again, is going to happen twice. First time, we're going to make a trans dibromide, a vinyl dibromide. Again, once we get to this stage, we're going to do it again just like it was a simple alkene. Add our second mole, and we get the tetra halide. Yeah.
What does vinyl mean, or is it?
Vinyl is a generic term for a double bond. So polyvinyl chloride, plastic, saran wrap, starts off as vinyl chloride, so ethene with a chlorine attached, one or chloroethene. That polymerizes. We'll do polymers next semester, and you wind up with long chains with chlorines on them, and that's your polymer. So vinyl simply means double bond.
Are we going to have to know it's a vinyl intermediate?
I probably won't ask for intermediates. There might be a multiple choice question or two that show up, especially on the quiz, that ask about intermediates like that. Now we get a little bit more interesting. This is a unique reaction of alkynes, but the chemistry follows very nicely from that of simple alkenes. If we had a double bond and we did mercuric acetate, we would get a Markovnikov alcohol, wouldn't we? So let's look at our alkyne here. Once again, you look at the two and decide the Markovnikov thing. This is the Markovnikov carbon, anti-Markovnikov. Again, Markovnikov's rule, whoever has the hydrogens will get the hydrogen. My rule is most stable carbocation. But okay, so if we just look at this and we did hydration, that is add water, we would expect our OH to go on this carbon. And by gosh, it does. This is what you form. However, this thing is called an enol. It is an alkene with an alcohol attached directly to it. Enol. Now the neat thing about an enol, and this will become extremely important next semester, is that this can undergo a simple reorganization to form a carbonyl compound. In this case, the carbon bearing the oxygen becomes a carbonyl. This becomes a methyl group. The tautomerization is called. Tautomerization simply means we change our bonding and move a hydrogen. We're taking this hydrogen and putting it here. We're taking this electron pair that was attached to the hydrogen and making a carbonyl. So bottom line here, you start off with an alkyne. You add water, and you wind up with a ketone. The oxygen is going to be bonded to the Markovnikov carbon. Enol intermediate, ketone as our product. Now, how do we do this magic? It's actually very, very simple. This is our enol. What happens is something will pull this proton off. These electrons will move in to form a double bond. These electrons in the double bond will move out, and they will pick up a proton. So the whole process looks like this. A base of some sort comes in. It can be anything, water. Pulls the hydrogen off, make our double bond, move these guys out, and we have our carbonyl compound. That's so neat. Let's do it again. Base pulls off the hydrogen. These electrons move in, these move out, and they pick up a hydrogen. Hydrogen goes here, and this is now a carbonyl. In like chapter 18 or 19 or so, we will see that anytime you have a carbonyl with hydrogens adjacent to it, that this is going to actually be an equilibrium between the enol and the carbonyl compound. Yeah?
Sorry, do you mind going back to the previous example of this? Can you explain how it goes from the intermediate step to the final step?
How we get from here to here?
Yes.
Okay, well, let's see. Let's say that we were just given this as a reaction. What you would do is you would say to yourself, I am going to simply add water, H2O, to my triple bond. I remember that it's going to be in Markovnikov addition. So the OH is going to go to the most stable carbocation.
Is that anytime you're adding an aqueous solution, it's always going to be.
Yeah, remember we have Markovnikov and anti. Okay, this is Markovnikov. So you look at this. This is the carbon that would give us the most stable carbocation. So when we add water, H2O, the oxygen is going to go to this carbon. And that gets us here. Now, the thing we have to realize is that it doesn't stop here. But that once we make the enol, this is going to rapidly convert to the ketone. But you can do this just in your head quickly by remembering we're going to get a ketone, going to get a carbonyl, and the oxygen is going to be bonded to the Markovnikov carbon.
Can you isolate the enol?
Hmm?
Can you isolate the enol?
No.
No, you can't.
You can actually detect it at equilibrium. And,
But you can't isolate before it turns into.
well, you can isolate an enolate anion, but that's chapter 19. So. Once we're at this stage, convert it to the carbonyl, pull off the hydrogen, move the electrons in, move the electrons out. Hydrogen goes here. This is now a carbonyl. On the exam, you will be asked to do something like this. You will be given an enol of some sort, and you will be asked to show by cute little curvy arrows to generate the carbonyl. Make sure that this makes sense to you. Remember with alcohols, or I'm sorry, with alkenes, we could make our alcohol either Markovnikov or anti-Markovnikov, right? For anti-Markovnikov, we used hydroboration oxidation. Exactly the same thing here for an alkyne. Exactly. We look at our alkyne. We identify the Markovnikov carbon. We realize that with hydroboration, the OH is going to go adjacent to it. So it will be anti-Markovnikov. Once again, we're going to add water, and that's going to give us an enol. The oxygen will be bonded to the anti-Markovnikov carbon. So just like an alkene. Now, this is still an enol. That means we're going to make this a carbonyl. This is going to be a CH2. Pick up a hydrogen, and by gosh, we made an aldehyde. This is an aldehyde because it has a hydrogen attached here. Don't forget the hydrogen. Yeah.
So this is still a reduction reaction?
Not a reduction, no. No, we're still hydrating. We're adding water.
And then, because for the last one, when we added water, we did Markovnikov, and now we're doing anti.
Right.
The only way to know is if, like, how do you know? Because for both of them, you're adding water, but for this one, you're adding boron also, or,
Well, you form a boron intermediate, but we get rid of it, remember, with the oxidation step. So, with an alkene, go back to last chapter, with an alkene, we can make alcohols, Markovnikov or anti. Markovnikov, we use mercury acetate. Anti, we use hydroboration. So same thing that you have to remember. If we have a hydrogen attached here again, this gives us an aldehyde. The simple thing is to just look at this and say, this carbon is going to wind up a carbonyl. It does so because we have the enol form on that carbon, double bond forms here to give us the carbonyl. We talked about catalytic hydrogenation or reduction with simple alkenes. Not a very glorious reaction. We simply converted the alkene to an alkane. If we do catalytic hydrogenation, that's with platinum or palladium, same thing. Get rid of our triple bond, we make an alkane. Exactly the same mechanism, just do it twice. However, with alkynes, we can stop the reaction halfway. There are two ways that we can do this. If we use what's called a poisoned catalyst. Poisoned catalyst simply means it's a really rotten catalyst. Really rotten. A Lindlar catalyst is what it's called. What you do is, instead of putting your platinum or palladium on carbon, you put it on barium sulfate. A catalytic converter in an automobile can go bad if you burn bad gasoline. If your gasoline has lots of sulfur in it, the sulfur will coat your platinum converter surface, and you wind up with something like a Lindlar catalyst that isn't very good. It's a poisoned catalyst. Well, if you do a poisoned catalyst with an alkyne, it's good enough to add 1 mole of hydrogen, but not good enough to add the second. Now remember, with an alkene, we put both hydrogens on from the same side, didn't we? Do the same thing with the alkyne, but that winds up, because we put them both on from the same side, we now have cis stereochemistry. So partial reduction, Lindlar catalyst, or you can remember platinum or palladium, barium sulfate. Probably on the exam, I would just go ahead and call it Lindlar catalyst. So this gives us our partial reduction with a cis isomer. We can also do partial reduction and get the trans isomer. Remember we talked about dissolving metal reduction. We took little bits of zinc or something and added it in acid and it fizzed, right? I said that it fizzed because it was making hydrogens, that were little hydrogen radicals running around. Well, if you do that with an alkyne present, typically you use lithium and you use liquid ammonia as your solvent. It fizzes. Again, we have hydrogen radicals running around. These add to our triple bond one at a time, but they add trans. So the neat thing here is, with a triple bond, we can do a partial reduction to give a cis isomer, partial reduction to give a trans isomer. We can do a full reduction to give the alkane.
Can you repeat that sentence, please?
Hmm?
Can you repeat that sentence? So with
Well,
the
I'm not sure I
triple
can.
bonds, you can do
With a triple bond, we can do a partial reduction with Lindlar catalyst to give a cis alkene, partial reduction with lithium liquid ammonia to give a trans alkene, or complete reduction to give the alkane.
Would you rather have it be a trans?
Well, it depends on what you're trying to make. I mean, that's the neat thing about organic chemistry. You have a target molecule you're trying to make, and you choose the conditions to make it. We'll see an example in just a bit of what a very, very classic exam question looks like for that reaction. All right, finally, we're going to do oxidations. Remember, if we had acidic permanganate, what happens with an alkene?
Okay.
We split it, don't we? If we have a double bond with acidic permanganate, we just break our bond. We're going to get carboxylic acids, ketones, CO2, whatever. With a triple bond, you're going to break it the same way, but you're only going to make carboxylic acids. This half, this carbon winds up as a carboxylic acid, this carbon winds up as a carboxylic acid. If we had a hydrogen attached here, it would wind up as CO2. So just like the alkenes. Learn it once, use it twice.
So what would be your major and minor product?
Hmm?
You have to know your major and minor product.
No, these would be formed equal. Because we're just splitting our double bond. Both carbons become carboxylic acids. All right. We will see questions on the exam that will be reactions. Pretend this is part of the exam. Write the products for these alkyne reactions.
Yeah.
Whoops. Yeah. Mm-hmm.
So, we went over yesterday,
No, that's a, this one, we're throwing it in the middle, just to make a ketone. And if this has a hydrogen, it'll be a carboxylic acid.
that's always the case for this, because you didn't do anything.
Yeah, we did. See, we have two hydrogens, two carboxylic acids. All right, our first one, we're going to add HCl. This is a symmetrical alkyne, so it doesn't matter where you put it, but we have to remember that both chlorines go to the same carbon. And that would be our product. Our next one, we look and we say, okay, hydroboration oxidation. I know that makes anti-Markovnikov alcohols, don't I? My anti-Markovnikov carbon is going to be this guy with the hydrogen on it. Now, because we're dealing with an alkyne, I know that this is going to give me an enol with the oxygen attached here. And that eventually this will show up as a carbonyl. So I will have a carbon-oxygen double bond here, 2 hydrogens here. And the product would look like that. Carbonyl here, 2 hydrogens here.
Where did the 2 hydrogens come from again?
1 hydrogen, well, we're adding water, aren't we? H2O. So, H2O. Our next one, we're doing reduction. We have lithium in liquid ammonia. We remember that that's going to be stepwise. It's going to stop halfway. It would give us trans stereochemistry, but we have a hydrogen here, so it doesn't matter. We'll simply make the alkyne. Yeah.
So because you have another hydrogen, the stereochemistry just doesn't matter?
Right. I mean, we did add these trans, but we have 2 hydrogens on this carbon now. So there is no 6 trans here. You can't tell. Hydroboration oxidation. We know this is going to be anti-Markovnikov. We're going to wind up with a carbonyl. That carbonyl will be on the anti-Markovnikov carbon, right? We have a benzyl carbon, don't we? Benzyl stands for supercarbocation, right? That's good. Therefore, this is our anti-Markovnikov carbon, simply bonded to the CH3. So this is going to be a carbonyl. This will be a CH2.
So in this one, it does matter where the CH2 goes.
Oh yeah. CH2 is on the Markovnikov carbon.
Secondary.
It's anti-Markovnikov. It's benzyl. Remember, the benzyl carbocation is very, very stable. Here we're just doing the addition of water in the presence of mercury. This is going to give us a Markovnikov alcohol, isn't it? So we look. Markovnikov counts hydrogens. So we expect the hydrogens to go here and the carbonyl to be formed here. Two hydrogens here, carbonyl on the Markovnikov carbon. It's always fun to put this one on an exam to see how people draw it. This is, again, the adamantane structure. Sodium amide, what we're going to do here is make the anion, aren't we? This anion is then going to attack the methyl group, bromine will leave. All we're going to do is add the methyl group here to make this compound.
What's that called?
Well, we'll see in chapter 10 that this is called an SN2 reaction. It's just a simple substitution reaction. And the one that you will see on the exam, I can guarantee you, looks like this. We have an alkyne, and we are reducing it 3 different ways. Draw all 3 products. Lithium dissolving in liquid ammonia is going to give us a trans-alkene. Going to add 2 hydrogens, stereochemistry, trans. If we do hydrogenation in the presence of platinum on carbon, we're going to go all the way to the alkane. Okay. Reduce our triple bond to the alkane. And finally, Lindlar catalyst. Lindlar stands for lousy. It will stop with 1 mole, but just like all hydrogenation, the hydrogens go on from the same side, so we have a cis isomer. Any questions? We'll see something very much like this. Make sure you can easily differentiate between the cis and the trans conditions. Simple alkyne, 2 moles of chlorine. We know that halogens add double bonds to give halides, dihalides. They add to triple bonds to give tetrahalides. I threw this next one in just to make sure you're paying attention. HBr peroxides, this is an alkene, remember? This gives us anti-Markovnikov alkyl halide, alkyl bromide. This would be our most stable carbocation. This would be the most stable radical. Therefore, bromine is going to add here.
And that's just because peroxide is present?
I'm sorry?
Is that just because peroxide is present? That
Right.
makes it anti-Markovnikov?
Right. Remember, HBr by itself gives Markovnikov addition. That would be here. With peroxide, you get anti, which is here. Once again, Lindlar catalyst. Lindlar, lousy. Going to get cis addition of hydrogen. And that's our compound. On the exam, you will see mixed all together, like these, all the reactions of alkenes all the reactions of alkynes. I know there's a lot. You'll probably have maybe 15, 16 reactions to do on this exam. I will give you a sample exam on Monday, and you'll see pretty much what we're dealing with. I can't give it to you now because I haven't finished it. I'm not sure I can finish it by tomorrow. You know, I have to draw all these little cute structures. It takes a long time. Yeah.
I'm still not understanding the Lindlar catalyst.
Lindlar catalyst. It's just a lousy catalyst. Okay, it's a poison catalyst. Remember with an alkene, we have the picture. The hydrogen comes to the surface. The alkene then comes to the surface. Then the hydrogen slips over on the same side and adds to the double bond. Because they slide over together, that means the hydrogens go on the same side. Same thing here. This sticks to the surface, so this hydrogen. Hydrogen comes into one face only. Because of that, these must be adjacent to each other.
So it goes, each hydrogen goes on either side of the triple bond, but on the same side.
Right, on the same side at the same time. It's just hydrogen's here, it's here, it slides over together. Must be on the same face.
That makes it good trans. That makes it good trans.
That makes it cis. Cis addition. All right, let's go ahead and do the last part. And this is the really fun part of organic chemistry. It's all fun, isn't it? And this is synthesis. This is reactions backwards. Now we're going to start off with baby synthesis. Not making babies, but baby synthesis. That is a single step. By the time you finish organic chemistry next semester, you will be doing synthetic conversions that involve 4 or 5 steps. That's really neat. Great thinking backwards. The way you do this is you look at your target molecule and you ask yourself questions. You say, what kind of molecule is it? How do I know to make that kind of molecule? What do I need as a starting material to do that? All right. Let's start off with this guy. We look at it and say, what kind of compound is it? Well, it's an alkyl bromide, isn't it? How many ways do we know to make alkyl bromides? We know 2 ways. Only 2. We can make a Markovnikov or an anti-Markovnikov alkyl bromide. Right? What is our regiochemistry here? The real question is the bromine attached to the carbon that would give the most stable carbocation? Well, it's attached to a secondary carbon, but this is tertiary, isn't it? So we would look at this and say, this is an anti-Markovnikov alkyl bromide. The bromine is not attached to the carbon that would give the most stable carbocation. All right, how do we know to make anti-Markovnikov alkyl bromides? HBr peroxide, right? If we took this alkene and we reacted it with HBr in the presence of peroxide, this would be an anti-Markovnikov reaction. Bromine would go here. This would be our most stable carbocation, most stable radical. Therefore, bromine will add here.
For the counting on that, where would you start? Right or the left?
Do you what? I'm sorry?
For counting, like you go 1, 2, 3, 4, and then you'd have 2 methyl.
Oh, you mean naming this compound?
No, on the right hand side.
This guy?
Yeah, that's a butyl. I mean,
It's a
butene.
1, 2, 3, 4, so it's a butene.
2.
This would be a 2-methyl-butene.
Alright.
So we looked at this. We said anti-Markovnikov alkyl bromide. I know I'm going to use HBr peroxide. All I have to do is write an alkene that would give me that product. What if I said, I'm going to write this alkene and do HBr? So not HBr peroxide, just HBr by itself. What if my logic was, Markovnikov tells me the hydrogen goes here, and the bromine goes on the secondary carbon? Would that work?
You'd have another extra
Nope.
hydrogen.
Why not? Because remember, these reactions, HBr and acidic aqueous acid, are going to involve carbocations, and they can rearrange. If we did this, we would get this as our carbocation. This will now undergo a spontaneous rearrangement. Hydride H- will simply move over to here, and we would wind up with the tertiary alkyl halide. Now, we're not going to do big-time rearrangements on the exam, but as we get more sophisticated, we will always be looking for rearrangements. Simple anti-Markovnikov regiochemistry. Let's do another one. Look at it and say to yourself, what type of molecule is it? It's a halohydrin, isn't it? We remember a halohydrin involves a bromonium ion, and the OH group adds to the carbon that would give the most stable carbocation. So, step 1, it's a halohydrin. Step 2, the hydroxyl group is bonded to the carbon that gives the most stable carbocation, which is our tertiary carbon. So write the structure of the alkene that you would need and the reaction conditions. Now I'll tell you a secret. When you get this exam, you will have simple synthesis reactions. A lot of times you can sit there and you can do this stuff, and then you scratch your head and say, well, wait a minute, what are the reaction conditions? Remember, if you flip the page over, you've got 15 or 16 reactions, don't you? With the conditions all there. So if you don't remember exactly what the conditions are, simply look at the reactions, find it, and put it in. Our double bond, this must be the alkene right here. Therefore, it must look like this. We're simply adding HOBr You could put it in BS water DMSO. Simply HOBr would work. You could also put bromine in water. But HOBr is the simplest. We look at it, we say to ourselves, what type of molecule is it? Well, by George, it's a trans 1,2-dibromide, isn't it? How do I know to make those? I add bromine to an alkene. Oops. What you need to do is simply think, what alkene do I need? And what reaction conditions? The alkene carbons must have been these two. And we're simply adding bromine.
Are we gonna have to like know these in like two-step processes? Like where it goes through one reaction and then through another reaction?
Not this semester, next semester, yes. All the way up to 4 or 5 steps. Something to always look forward to. All right, what kind of a molecule is it? It's an alkyl bromide, isn't it? Is the bromine attached to the carbon that would give the most stable carbocation? Well, bromine's attached to a tertiary carbon. That's a secondary carbon. So yes, it is. This is a Markovnikov alkyl bromide. So we could make this simply by the addition of HBr to an alkene. Go ahead and write an alkene, that'll work. Well, this one is simple. I just put my double bond here, and I'm going to add HBr. HBr, the bromine will go to the Markovnikov carbon, hydrogen will go here. However, I can also use this alkene. So a double bond on one of these carbons. Once again, Markovnikov carbon, hydrogen goes here. I could also use this alkene. Now, that might be surprising unless you think about it. This would initially give us the carbocation here. Rearrangement would put the carbocation here, and that would give us this product.
So there's 3 different ones because there is rearrangement.
Yep. 3 possible answers. On the exam, don't do something that requires a rearrangement. Okay, stick to the simple Markovnikov. On the exam, I would of course give full credit, but don't do that to yourself. Just stick to the simple Markovnikov pair. Another way that you see synthesis on an exam And these other ones I said, make up your own starting material. Here, I give you starting material, and I say, make this for me. So you choose one of these guys. But it's going to be the same logic, isn't it? So we look and we say, it's an alkyl bromide. Is the bromine attached to the most stable carbocation? No. This is a tertiary center. This is a CH2.
Okay.
Therefore, it's an alkyl halide, and it's anti-Markovnikov. If we did addition of HBr to this guy, the bromine would go up here with it. If we did anti-Markovnikov addition here, the bromine would go on the secondary carbon. But if we use this guy, we're adding to the end. These two don't have double bonds at all. This one does. This is the compound you want. Reaction conditions. We're trying to make an alkyl halide with anti-Markovnikov. Regiochemistry, that is simply HBr peroxide. What if I asked you to make this? This is an alcohol, isn't it? And the OH group is attached to a tertiary center. That's the most stable carbocation. Correct? Therefore, we have simple Markovnikov regiochemistry. We're adding to our tertiary carbon. So this guy, and this guy. These two, very clearly, we could add aqueous acid. The OH would go to the tertiary carbon. With this one, we would form a carbocation here, but it would rearrange to the tertiary carbocation. Therefore, all three of these would give the desired product. I wouldn't choose this one on the exam. Both of these would be equivalent. You still get credit for it.
If we use what? Can you go back to that little
Add to the tertiary. Both of these, Markovnikov regiochemistry, put the OH here. This one we could do it with a rearrangement.
So 2 and 3 work better than 1.
Yeah. This is clear. If we wanted to be really clean about it, instead of using sulfuric acid, which is ugly, we could simply use butyric acetate and these two to cleanly give us the tertiary alcohol.
So the acid just breaks the double bond.
Yeah, we simply add water to the double bond, H2O. Let's do another one. What type of compound is it? It's an alkyl bromide. Is the bromine attached to the carbon that gives the most stable carbocation? No. It's attached to a secondary, there's a tertiary. This is anti-Markovnikov.
In this case, like, how do you know to distinguish versus anti and then Markovnikov?
Well, you look at your whole molecule. Is the bromine attached to the carbon that would have given the most stable carbocation? That's all. No, it's not. That would be here. We're attaching to the secondary carbon. So these guys of our two candidates, we could do anti-Markovnikov addition here. This would be a Markovnikov addition, wouldn't it? And it would rearrange. So the only one that works here is this guy. And we simply want to make this with HBr peroxide. Couple more of these. It's an alcohol. Is the OH attached to the carbon that would give the most stable carbocation? Oh, it's attached to a CH2. There's a tertiary carbon. So this is an anti-Markovnikov alcohol. How do I know to make anti-Markovnikov alcohols? Hydroboration, oxidation. My OH is attached here to a primary carbon adjacent to the tertiary carbon. So the ones we're looking at would be these guys. These don't have double bonds at all, so this is our only real candidate. So we'll use this as our starting material. Our conditions: hydroboration, oxidation. If you forget what to write, look at the reaction page. It's going to be BH3THF followed by oxidation. Yeah.
So like,
Just add
so
it
you
to the
would,
chain.
because there's an intermediate step in there.
I'm sorry?
Isn't there an intermediate step in there? You don't have to show that, like.
But you don't have to show the borane intermediate.
Okay.
One more of these. I'll hush for a second while you do all the logic. Is the bromine attached to the most stable carbocation center?
Yes.
Absolutely. So we're going to simply add HBr, aren't we? We know that we're going to add to our tertiary center. So that's these guys. But because we have a carbocation intermediate, even though there's no double bond here, we could still get rearrangement. These two are probably the best candidates, but all three would work. simply want to add HBr as our reaction conditions.
You have to rank your like
Nope, nope.
which one would be most favorable.
You just simply, on the exam, you would simply choose any one of these, only one, and put your conditions. Now there's one more way that this is shown on an exam. It's a little more versatile because it covers lots of different functional groups. Here we have a large selection of starting materials, and we have a target. But the logic is going to be the same thing. We're going to look at our target, we're going to say, what is it? How do we make it? And then we go and we look up top to see what would work. This is actually easier, I think, than the other. So let's do it. This is a 1,2 diol, isn't it? And they are on the same side of the molecule. It's a cis 1,2 diol. Now, how do we know to make cis 1,2 diols? Alkaline permanganate, right? It's the only way we know. We could use osmium tetroxide too, the same reaction. Okay, so we're looking for an alkene. The compound we're looking for must have 1, 2, 3, 4 carbons and a double bond. So we look at our selection up top. We also note that our methyl groups here are on opposite sides of our molecule. So we're looking for 4 carbons. Our methyls must be trans. Well, our 4 carbon backbones are going to be these 3 molecules. This one we can rule out right away, right? Doesn't make sense at all. We know no way to do this. These 2, we have methyls that are trans, methyls that are cis. Again, look at this. Hydroxyl groups are on the same side. Methyl groups are on opposite sides. So they're trans. So, we're using this as our starting material. Again, our reaction conditions. Either osmium tetroxide or the simplest, alkaline permanganate.
Could you reword the compounds being used to make the same reaction?
I'm sorry, can you what?
Use like something else but does the same thing, like the compounds being used to create the reaction.
What, this guy you mean? This is the
Got
only
HO
alkene that will work.
and then O4, whatever that is.
Permanganate.
Could you use something else though?
Osmium tetroxide followed by sodium bisulfite would also work. But it's the same reaction. This is the one you want. It's the simplest. Easiest to remember. Oh, we're making an aldehyde. We learned how to make aldehydes today, didn't we? The way we learned today was by taking an alkyne and adding water. We could do that in a Markovnikov fashion or anti-Markovnikov. Is the oxygen attached to the carbon that would form the most stable carbocation? This is
Primer.
a primary carbon? No, because this is a secondary carbon. So this is anti-Markovnikov. But that's okay, we know how to do that. Hydroboration, oxidation of an alkyne. We have 1, 2, 3 carbons. So we look at our menu here and find something with 3 carbons. Aren't too many choices, are there?
1, 2, 7.
Just that one. See how simple that is? And our conditions. We want anti-Markovnikov, so it's simply hydroboration, oxidation. Carboxylic acid. We actually know a couple ways to make carboxylic acids. We can oxidize and split an alkene, or we can oxidize and split an alkyne. What you need to do is look up top and try to find something that we can split, either an alkene or an alkyne, that will give us this guy. We're looking for a 2-methyl-butane backbone. Now, we look up top. Only one that works is this guy. Remember, we're looking for an alkene or an alkyne that we can split. The only one that has the carbons we need is this. Our reaction conditions. To split an alkene or an alkyne, we simply need acidic permanganate. Alkaline permanganate gives a diol. Acidic splits. Different set here. Making a simple alcohol. It's a 1-methyl cyclohexanol. We don't know how to name it yet, don't worry. All right, so it's an alcohol. This is bonded to our tertiary carbon, so it's Markovnikov. We need to find a 6-membered ring we can work with, right? Up top, we have 6-membered rings here and here. Which of these do you want to choose? Because this is Markovnikov, actually either one of these would work. Because this guy would give a rearrangement, but this is the simple one. All we need to do is add water. We can either do this with strong acid or with mercuric acetate.
Why won't the one with the circle work?
This guy?
No, the one with the light. I see.
Yeah, this guy we would get a rearrangement.
What's
Try to
the,
avoid rearrangement.
what's the circle within the ring name?
Oh, this is a benzene ring. Chapter 12 or something like The nice thing about showing the benzene ring with a circle is that you don't confuse it with an alkene. All right, what if we did this one? This is an anti-Markovnikov alcohol. How do we know to make anti-Markovnikov alcohols? Hydroboration, oxidation. Again, we need a cyclohexene to work with. We have 2 cyclohexenes. Which one do you want? Anyone want to vote for the bottom? Problem with the top is that these are both secondary carbons, aren't they? So there is no clear Markovnikov, anti-Markovnikov. In fact, with this one, the alcohol would almost always wind up here because the methyl group gets in the way. This guy, this is our Markovnikov carbon, so the OH would go here. Remember, in hydroboration oxidation, the hydrogen and the OH go on the same side of the molecule. So they are cis to each other. And our conditions are simply this. Let's do one more. This is an alkyl bromide. What's our regiochemistry? Is the bromine attached to the carbon that would give the most stable carbocation? No, that's a benzyl group, isn't it? Therefore, we are looking for something with a benzene ring. We're going to use HBr peroxide to get anti-Markovnikov regiochemistry. With our arene or benzene background, we have 2 possible arenes. This guy doesn't have enough carbons, does it? So the only one that would work would be this guy. And our reaction conditions are simply HBr peroxide. Any questions? All right. On the handout, there were a couple other syntheses shown that I forgot to